Welcome to Quantum Curious, and today we are going to discuss two important concepts related to photo detection. So the first concept is the variance of the number of photo counts, that how the photo counts are distributed when they are detected, and their variance. And also we are going to discuss the quantum theory of photo detection, in which we are considering the quantization of the light field in consideration as well with the quantization of the detectors. So moving on to first the variance of the number of photo counts, that how the detected photo counts are distributed, uh, and how and which kind of physical insights they are providing us with. So we can calculate the variance of the photo counts with the equation given in equation 1, and we know that the average of the photo count is uh, directly proportional to its the intensity of the light field, and it is multiplied by the efficiency, that is the eta of the photodetector. So our first goal is to calculate the average of the n square. So it could be calculated by the formula given in equation 2. So we know that the probability distribution followed by the photo detector detection is given by the Poisson distribution, as it is a random process. So we are going to use a trick to calculate the the average of the n square. So we are going to use this kind of trick, so we do not have to use or calculate this quantity, that is the npn. We know that it is proportional to the intensity of the field, and the proportional to the uh, a constant, and that is the efficiency of the photodetector. So we are going to calculate this. So calculating this first term in the expression, so we can make use of the, again, probability distribution of the photo detection, that is the Poisson distribution, and making use of the factorials and expanding the factorials in denominator and canceling out the common terms, we came up with this expression. So we have taken out an eta I square term outside the sum, and we are end up with this. So we can make use of the change of the variable, as will it will not change the overall physics of the problem. So we know that it is exponential with eta I, and it will cancel this exponential, that is having a minus sign in its power, and we are end up with this expression, is this expression at the end, that is the eta I square. So the average of the n square is calculated as this, that is the first term from there in equation 3, and we know that the average of the photo count follow this mathematical form, that is the average of the intensity and with the constant, that is the efficiency of the detector. So putting all this in equation 1, we are end up with this, and we know that this quantity can be uh, taken common with by taking eta square as a common, and we are end up with the variance of the field, or variance of the intensity of the field, that is the fluctuation of the field. So the variance of the, or the fluctuation of the photo detection is depending upon the two terms, that is the average of the photo detection and the fluctuation of the field. So it will have some application in the results, and it will vary from field to field. So for non-fluctuating field that has no fluctuations in intensity, like we have laser, so the average, the distribution or the fluctuation of the photo detection will follow minimum quantity that is the short noise, and it rises due to the random process of the detection of the uh, light by photodetectors, and it is usually called the short noise, and it is a minimum classical noise that we have to face during photodetection process. So we will see later in later sessions that it could be minimized and by using some kind of special state of light like squeeze state, but we will see it later. So for fluctuating field which has non-zero fluctuations of the intensity, the fluctuation of the photocounts is greater than the short noise, and we have another term that is the wave noise, that is related to the uh, noise of the wave that we can associate it. So the for fluctuating field, uh, the noise in the photo detection is much larger than the short noise, because we have also the noise from the fluctuation of the intensity field itself. So this is the classical notion of the photo detection, and the noise is associated with the whole process. So we are going to move to the quantum theory photo detection, and in which we have to consider the quantization of the incoming field as well as the quantization of the photo detector. So we know that the probability of a state in finding the probability of the state in a certain state like n can be calculated by the equation 5. So we have a state psi rt, and the probability of that state to be found in the state n is given by equation 5, and it could be related to the initial state of the system by equation 6, and it is a perturbation solution of the Schrödinger equation, and the probability of the transition of the photodetector, that is the electrons of the atom, can be calculated by 7. So we have electrons in psi 0 state at the initial time, and they are absorbing the field, and the probability of finding them in state n later could be calculated by equation 7. So we know that we do not know in which state the electrons are lying, so we have to take the sum over n, and we end up with the equation 8. So we could expand the modulus square and end up with this equation, and we have both parts of the complex amplitude field, and we can denote this whole uh, sandwich expression, that is the kind of average, by first order correlation functions. First order correlation function is describing the coherence of the field at a specific point at specific time interval. So it could be denoted as the average of the field of the average of the field at a point, at a certain point, and at a certain time. So it could be calculated in laboratory by calculating or measuring the incoming field. So the first order correlation function is given in equation 9, and as we described earlier, it tells us that how much the coherence in light is, and it basically tells us the intensity of the field and how much is it fluctuating. So in order to find the joint probability of the system later at time t, in order to be found in different state at m, at different position at r2, and this could be calculated by this joint probability formula, and it is just telling us that uh, the probability of finding the state at different position at different time and when it was first detected in state and later at the time uh, at the initial time T1 at different position R1. So it is giving us the sense of the statistical property of the light, and we are uh, we are uh, somehow describing that how the detection or process of the at the two position and at the position at the two positions at the two different interval of time are correlated with each other. So this quantity is usually denoted as the second order correlation function. The second order correlation function uh, is given as in 11, as in equation 11, and it is usually the average of the product of the uh, intensity of the field at at different position and at different time, and it gives us the statistical insight about the light and some processes like anti-bunching and bunching of the light field. So the second order correlation function could be calculated experimentally. And this is the experimental setup that could be employed to measure the second order correlation function. So we have a light beam or signal beam, and it is divided by the beam splitter, and the beam splitter is the ballast beam splitter, that is it is reflecting and transmitting equal uh, the it is transmitting and reflecting the light with equal intensity, and detector 1 and detector 2 are measuring the relative intensity of these two fields. So output is giving the product, the average of the product of these two intensity, and it is giving us the notion of the second order correlation function. So for the complete description of the light, that is the statistical properties of the light can be inferred from the first order and second order correlation function. And we usually do not need with the correlation function with much higher order, because it is also difficult to implement due to the present day technology, and we usually do not need that much of information to describe completely the given field of light. So usually in laboratories we usually uh, are satisfied with the first order and second order correlation function, and these two quantities are enough to describe the statistical properties of the light and to describe fully the given state of the light. So this is for today. We describe the fluctuation of the photo counts for the classical field, and we also saw that how the quantum description of the photo detection could be written by considering the quantization of the light with the quantization of the fee of the photodetector. So these kind of concepts are usually helpful in describing the state of the given light, and we will see much later how these concepts are helpful in describing different properties of light like anti-bunching and bunching of photons. So thank you for listening all these, and if you like, kindly share and do comment below, uh, and that is so